So today we are going to look at ionic equilibrium, and specifically we are going to look at the acid dissociation constant, that is Ka. And we are going to consider a weak monobasic acid, that is Ha, and we are going to see how it's going to dissociate in solution. So if you are having our acid Ha, it's going to form hydrogen ions. Because it's monobasic, it's going to form one hydrogen ion plus A negative. So in here we are going to apply the law of mass action, which, and in this case our K here is Ka. So we're going to say Ka equals, remember mass action is the product of the concentration of the products divided with the concentration of the reactants, and in this case our products is hydrogen ions and this A. So I'm going to say A aqueous, so multiplied with A aqueous divided by this. So here we are using the concentration brackets. So in this case, we are seeing how Ka is relating with the hydrogen ion concentration and the acid concentration. But we can also have, if it was ethanoic acid, so it can be like this. So it will form the ethanoate ions plus hydrogen ions. So our Ka will be ethanoate ions, hydrogen ions, divided by the ethanoic acid. So let's look at the relationship between Ka and degree of ionization. So let's consider ethanoic acid in solution is going to ionize to ethanoate ions and hydrogen ions. So if we are to consider the initial mole, it's going to be 1 for the reactant, and the products we shall not have any at the start of the reaction. So if we are to consider the moles at equilibrium, so if you say that at equilibrium we are to form alpha ethanoate ions, alpha. Remember the mole ratio is 1 to 1, it means even hydrogen ions are going to be alpha. So if our initial mole was 1, so the moles of ethanoic acid at equilibrium will be 1 minus alpha. But remember our acid is of concentration C. So we are going to multiply these moles with C. So in here we are going to apply the law of mass action again, which is Ka, which is the product of the concentration of the products, but in this case we are going to consider these moles here. So it's going to be C alpha times C alpha out of C into 1 minus alpha. So this is going to cancel with this. So we shall end up with Ka equals to C alpha squared over 1 minus alpha. But we know for a weak electrolyte or for a weak acid, we have few ions, meaning ionization, we form few ions. So in this case, 1 minus alpha is almost 1. Because this alpha is going to be too small, so we shall end up with Ka equaling to C alpha squared. So we can have our expression here, we can use it in calculation, but also we can look at how we can get hydrogen ion concentration using alpha. So if we look here, hydrogen ion concentration equals to C alpha. And if you are to remember, pH equals to negative log of hydrogen ion concentration. So we can feed pH equals to negative log of C alpha. So let's solve this task. The acid dissociation constant of 0.1 molar ethanoic acid is 4.39 exponent negative 5 at 25 degrees Celsius. So they want us to calculate the degree of ionization. But we earlier said the degree of ionization from Ka equals to C alpha squared. So we are having Ka, which is 4.39 exponent negative 5 equaling to C, which is concentration 0.1 molar alpha squared. So our alpha equals to the square root of 4.39 exponent negative 5 out of 0.01. So our alpha equals to 0.066, but we can represent this alpha in form of percentage, which is alpha equals to 6.6%. You just multiply this with 100. So this is our alpha. So we can also use this knowledge of alpha to determine the pH of the acid. Remember, pH of the acid equals to negative log of hydrogen ion concentration. So after getting this hydrogen ion concentration, remember the concentration of hydrogen ions equals to C alpha. So our pH is going to be negative log of C alpha. So our pH, we are going to feed our values equals to negative log of C, which is 0.01 times our alpha, which is 0.066. We don't use this one in percentage. You have to first convert it back to moles. So our pH equals to 3.18, and pH doesn't have units. So this is our answer.